Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. The Weil conjectures concerns counting solutions to polynomial equations over a finite field, or equivalently, counting the number of points on a variety over some finite field, say FQ. So this is the notation for the finite field with Q elements. What I want to show you in this video is how we can package that information in what's called the zeta function. Okay, so let's start with the definition of the zeta function I want to use, and there are actually a couple used in the literature, but this is the one that I want to present here. So suppose x is some variety over fq. So in other words, this is just something that's contained inside either the affine space or in projective space, and it's carved out by a finite number of polynomial equations, homogeneous equations in the projective case. Okay, and we just want to look at the points on this variety. Okay, so this is something that's defined by polynomial equations with coefficients inside this field. Okay, so of course you can solve it not only in this field but also in any field extension. So in particular, if you pick any r which is a positive integer, you can look at the field fq to the r, so that's going to be a field extension of fq, and you can look at the fqr points of x. In other words, solving those polynomial equations which have coefficients in fq, but you solve them in this field here. Okay, and you can look at, count the number of these solutions. Okay, so the number of solutions here will be finite, because even if you're looking in either the affine or projective space and you have coefficients or entries rather in a finite field, then there can only be finitely many of them. Okay, so we're going to let nu r denote this number. Okay, so of course this is going to be an increasing function. As you increase r, you're increasing the size of the field, so you can get more and more solutions. And you want to see basically how that grows. So this is the data that I want to package. And the way I'll do it is by introducing this generating function, this zeta function here, z subscript x of t. So what we'll do is we'll make this function as follows. We look at firstly this power series, the sum from r equals 1 to infinity of nu r t to the r over r. And then we take that power series, okay, which has zero constant term, and we exponentiate it. Okay, so it looks like a bit of a funny thing to do. So let's just think about it. So essentially what you have is you have a power series, okay, in t, and the coefficient is given by nu r on r. You take that power series and then you exponentiate it. So before we try to explain why you might want to do something like that, let's have a look at a simple example. And the simplest example here that's quite illustrative is to look at x equals the projective line. So remember, the projective line is the same as the affine line, which you can think of as a copy of the field, okay? And you take the disjoint union with a point. So what's nu to the r? So the affine line, okay, if you look at the affine line, the points of that over fqr, of course, they're just q to the r of them. And then there's an extra point at infinity, so you add 1 to that. So that's my nu r. Let's work out what the zeta function for p1 is. Okay, so what I want to do is I want to take the exponential, and I form this power series where the nu r now is this number here, q to the r plus 1. So what's rather nice about this and the way I've written it is that you have a sum here, so you can break this up as two sums. Okay, so one with the qr and one with a 1 term. Okay, and since exponentials take sums to products, you'll get a product of two exponentials now. The first term corresponding to the qr here, you get qr t to the r, you might as well write it as the rth power of qt, so that's divided by r, and you have this exponential term here. And then you have the exponential term of just 1 times this. So that's a sum from r equals 1 to infinity of t to the r on r, t to the r on r. But what's rather nice about this is that hopefully you can see that this is a well-known Taylor series. Okay, so what's that? So this is essentially just, well, you take the negative of the log of 1 minus t. Okay, so that's rather nice. So that means that when you exponentiate this, well, firstly, you can, the minus means that you have the inverse of the exponential of this log. And so you have the inverse of 1 minus t. So you have 1 and 1 minus t, and you multiply it by this exponential term here. But this is exactly the same, except for the t here is replaced by qt. So you replace the t by qt, so you have a factor on the bottom now of 1 minus qt instead. So this infinite sequence, okay, which corresponds to just this infinite sequence q to the r plus 1, is now packaged in this series here, okay, this function. And what's rather nice about this function is that, well, this is just a rational function in t. Okay, it's a polynomial in t divided by a polynomial in t. And the first part of Weil's conjecture is that this zxt, okay, is always a rational function over q. Okay, so just like in this case here, you have a rational function in q. In fact, this is general phenomenon. Okay, so the other question you might ask is that, well, why are we using the term zeta function? Okay, perhaps you've met Riemann's zeta function, which is extremely important in number theory. And what's the relationship to that? So let me show you what the relationship is in the simplest of cases, at least. Although this argument will work quite generally. Okay, so but for now, let's suppose R is one of the following two Dedekind domains, either Z, okay, or let's look in the special case where x equals a1, and there the coordinate f of this a1, okay, over fq is just a polynomial ring fqx. Okay, so they're both Dedekind domains. More generally, this argument will work if you replace the z here with any ring of integers, for example, the Gaussian integers, and this fqx can be replaced with the coordinate ring over a finite field of a smooth curve. Okay, so that's the kind of general setting that we can look at. Okay, so the first thing I want to do, so something that works in both these two settings, is that suppose you have a maximal ideal P inside R. We're going to introduce the norm of this P. Okay, so what's the norm of P? Well, basically you're going to look at R mod P, and in both these cases this will be finite, R mod P. Okay, if you have a maximal ideal inside here or inside here, okay, the corresponding quotient will be finite, so you can count the number of elements, and that's called the norm of P. Okay, so if you don't understand why that's true in the second example, let me look through that in greater detail for you. Okay, so suppose you have now P is a maximal ideal inside this polynomial ring fqx. So this, remember, is in fact a principal ideal domain. So it's generated by a polynomial, a single polynomial. And this is well defined up to non-zero scalar. Okay, so in particular, you can talk about the degree of that polynomial. We'll let that be d here, the degree of the polynomial. And that's also, you can say, is the degree of this ideal. It makes sense to define that because the only way you can change that is by some non-zero scalar. So that's the degree of P. Okay, so in this case, what happens if you look at this quotient here, R mod P? So fqx mod P. Okay, so this is a maximal ideal, right? So this has to be a field, okay? And it's going to be a field extension of fq. And the other thing that you should know, hopefully, if you know your ring theory, is that this is going to be an extension of fq, and in particular, it's going to be a extension which is a finite field extension, and the dimension of that is just given by the degree of this polynomial P. So it's a degree d field extension of fq, so it must be the field with q to the d elements. Okay, so as a vector space, it's just d copies of fq, so this field is the field with q to the d elements. So that tells you that the norm of P in this case is q to the d. Okay, so the possibilities that you can get for this norm of P, in this case here, are just various powers of q. And that power of q is just given by this, the degree of the polynomial, which generates that maximal ideal. So very important for our study of relating Riemann's zeta function, and that point of view with the zeta function that we've got in here, is this little fact here. Okay. So we can consider these maximal ideals. So here we're looking in this situation, we're considering maximal ideals of this ring here. And here we're looking at points. Okay, so we want to relate these two ideas. So how does that work? Okay, so firstly, if you have this ideal here, you have this polynomial, and you can look at its d roots. The d roots, where will they be found? Well, by Galois theory, actually, you can say that all the roots will be found inside fq to the d. So you can think of this as these d roots of this polynomial p, they correspond to d points of the affine line. Okay, d points of the affine line, and that's defined over fqd. Okay, so this is a very, very key point. That's how you relate this idea, where here you're looking at maximal ideals, okay, and here you're looking at points. Okay, we'll see this more when we go through the following wonderful proposition. Okay, so now we can define what gives Riemann's zeta function and generalizations of it. Okay, so what's zeta rs? Okay, so what you do is you take an infinite product. Overall P will be a maximal ideal of R. Okay, and you should look in a situation where all these maximal ideals are cofinite, so we can talk about the norm of these maximal ideals. Okay, and we have a product over that of the inverse of 1 minus the norm of P to the minus S. Okay, so let's have a look and see what happens when you look at the case of R equals the integer Z. Okay, so I claim that we recover Riemann's zeta function. So what's Riemann's zeta function? So here you look at all the maximal ideals of R, they correspond to the prime numbers. Okay, so you look at all the prime numbers, and what is this? 1 over 1 minus, so what's the norm of a prime number? Okay, so the norm of a prime number, okay, is just Z mod the ideal generated by that prime number, and of course that equals that prime number P. So this norm of P in this case is just P. So you have 1 minus P to the minus S, and this is the usual Riemann zeta function. Okay, so what's the relationship now? So we've defined the Riemann zeta function, the usual one, here, and we've managed to find a definition which incorporates also the case where you can take R to be this coordinate ring of the affine line. So in other words, a polynomial ring fqx. Okay, so this is a function of S. Okay, this I've written this zeta function here of A1, I've written as a function of t, but I claim that if you take the change of variable t equals q to the minus s, then you will get this version of the zeta function. Okay, so that's what I want to show you now, is how the notion of zeta functions for varieties, as I've defined here, is connected to a more familiar one that you might have seen in number theory. Okay, so Riemann's zeta function here. Okay, so what do we need to do? Okay, so what I want to do is basically the change of variables here is t equals q to the minus s. So maybe I'll write that in so that you can kind of see that this is t is going to be the q to the minus s here. Okay, that's what you have. So what I want to do is on this side, I'll have that. But what's on the other side here is I have this term here. So let's have a look more closely at this term here. Norm of p to the minus s. What's that equal to? So what's the norm of p? Okay, so the norm of p is going to be here q to the d. So q to d, if you take q to the d to the minus s, that's q to the minus ds. Q to the minus ds, which is also the dth power of q to the minus s. So it's the dth, which is the degree of pth power of t. So if you write this out, this is just a product over all these p's, these maximal ideals p, are 1 on 1 minus, and if you change q to the minus s to t, it's just t to this d, which is the degree of p. So I've just basically changed variables from q to the minus s to t, and I want to show the corresponding equation here in terms of the t's instead. And this left-hand side, where I've rewritten this in terms of t, I've going to call y of t. Okay, so this is rather interesting. Here we're looking at maximal ideals. Okay, that's how this version comes into play. In this one here, we're counting points. So we want to relate those ideas. So here what I want to do is now count maximal ideals. And this is quite a tricky problem. And this argument shows you one way of doing it. Okay, so it turns out that, of course, in this case here, this ZA1T, okay, we did something more complicated. We did ZP1 of T, so we can easily understand what that is. But on this side, it's more complicated. Okay, How do you work out what are the maximal ideals of FQX? Okay, that's not such an easy thing. But this argument shows you a way of doing that. Okay, so what we'll do is we're going to say, okay, so let's look at all these maximal ideals P inside FQ of X, which have some specific degree D. Okay, so we're going to look at essentially count the number of, if you like, monic irreducible polynomials of degree D, and they're going to be irreducible over FQ. And we'll call that number mu D, okay, and we can let mu D grow. And basically what we want to do to relate these two sides is here, the important thing will be the mu Ds, and here, this is defined by the new R's. I want to find a relationship between the two of them, and this is the relationship that I want to give. Okay, that new R is given by the sum of D mu D, where D varies over all the divisors of R. Okay, that's what I claim is happening here. Okay, so why is that true? So the key point here is that firstly, when is FQD contained inside FQR? Okay, so FQR is an extension of FQD if and only if D divides R. So that's the key point. Okay. So what's the correspondence that I want to use? The correspondence I want to use is essentially the one that I gave here. If you have a maximal ideal, okay, each maximal ideal here, okay, will give you a number of points. And the number of points it will give will be D, where D is the degree. Okay, so that's the first point. Conversely, if you're given a point inside some FQ D here, okay, how do you go back and get a maximal ideal? Well, what you can do is you can take its minimal polynomial over FQ, okay, and that'll be given by FQD. Okay, so if you're inside FQR, okay, you can take it's a minimal polynomial, okay, and the minimal polynomial has to be, since it will give you some FQD inside FQR, the minimal polynomial will have D dividing R, okay. So that's what you'll have. And so there are D such elements, okay. So when you want to work out the number of points over nu R, okay, what can you do? You can kind of collect them together. All the ones which have the same minimal polynomial, okay, so maybe that minimal polynomial has degree D, and that D will divide R, you collect them all together, and there'll be D of them, okay? So, and those D will correspond to a single maximal ideal, okay, given by that minimal polynomial. And there are mu D such polynomials, okay, mu D such maximal ideals, so there'll be D mu D contribution from that, and you have to look at all divisors D of R. And that gives you this relationship here. Okay, so you might need to think about that a little bit more, but that's all the elements that's involved to prove this wonderful relationship. And this is the relationship that we need to establish this fact here. So the way we're going to do this actually is we're going to take what's called the logarithmic derivative of both sides here, show that they are the same, and then of course you can integrate back to check that they're the same just by checking in fact the constant term or they're not held by a constant. Okay, so let's look at the left hand side here and take the logarithmic derivative of this. Okay, and the logarithmic derivative, actually I'll multiply by t as well, so it's t times d dt of the logarithm of y of t. What's that? So the t dt is here, and we take the logarithm of this term here. Okay, so what I'm going to do is I'm going to collect in this product all the maximal ideals which have the same degree, so where this degree p is constant. For all the ones which have degree d here, okay, we're going to collect them all together. There are mu d of them. So there'll be, when this is equal to d, there'll be mu d such terms. So the contribution for that degree d is going to be 1 minus t to the d to the negative, so this is the inverse, so it's negative mu d. And now you're going to take the product over all positive integers d. Okay, so this is quite easy enough. What you do is you just take the logarithm of this. It takes the product to a sum from d equals 1 to infinity. And then you take the logarithmic derivative of each of these. So the logarithm of the minus mu d, you can bring out a negative mu d. Okay, so there'll be a minus sign, which will get cancelled later. And then you can differentiate this term here, when you differentiate the 1 minus t to the d, or the logarithm of 1 minus t to the d rather, you get the derivative of the logarithm gives you the inverse, so there'll be 1 minus t to the d here. And there's also a derivative of 1 minus t to the d. So there'll be a t to the d minus 1 times the t will give you the t to the d. The derivative of the t to the d also has a d term here. And there's also a negative term which cancels with the negative that you get from here. So at the end of the day, you get this power series, the sum from d equals 1 to infinity of mu d times d t to the d divided by 1 minus t to the d. Okay, so that's the logarithmic derivative of this term here, which corresponds to Riemann's version of the zeta function. What about the version that we have here, the zxt? Okay, so let's look at za1t and look at the logarithmic derivative of that. And now you can kind of see why we've defined it this way. When you take the logarithm of this goes, and you're just taking the derivative of this term here. So you'll get r cancels with that. So you get nu rt to the r minus 1. But you're multiplying by t, so you'll just get the sum from r equals 1 to infinity of nu rt to the r. Okay, so that's the term that you have here. And now remember, you want to equate this with this. Okay. So how do you swap the nu's to the mu's? Okay, so the nu r equals the sum from sum over all divisors d of r of d mu d. So you're going to replace the nu r with the sum of all divisors d of r of d mu d t to the r. And then the last thing that we need to do to identify this with this is we need a change of variables. Okay, so the change of variables that I want to use is that, well, if d divides r, that means r has to be a multiple of d. Okay, so you might as well sum over, well, let the new variable be r divided by d. Let's call it m. So firstly, you'll sum over all d equals 1 to infinity. And let's pull out that term here, d mu d. And then sum from m equals 1 to infinity. Remember, m is just d on r on d, so r is md. So that's t to the md. And now all you have to do is realize, well, this is starting to look a lot more like what you have here, but it's a double summation. There's the mu d here, there's the d term here. And this here is just a sum of a geometric progression. And the common ratio is t to the d. Okay, so hence a 1 minus t to the d in the denominator. Okay, and also the initial term is t to the d. Okay, so you have a t to the d here. And hence these are the same. And then the only thing that you need to check is that, well, of course, you performed a derivative to check that they're the same. So that's on the logarithm, so you should check that they're not off by a scalar. But it's quite easy to check, well, in this case here, if you look at this, when you expand this out as a function of t, of course, you're multiplying a lot of series. Each of these is of the form 1 plus, so this is a geometric progression, so it's a 1 plus and then higher powers of t. Okay, so there's 1 is the constant term here, and the same is true here. Okay, when you look at this is exponential. Here, what you have inside this part here is something that only involves t's. Okay, so there's no constant term, so 1 is the constant term here. So actually, these are the same, and that establishes this proposition and also tells you why we call it the zeta function. So one of the things that's extremely important and interesting about Riemann's zeta function is the fact that it satisfies a functional equation. And the second part of Weil's conjecture is that, well, if you have x as a smooth projective variety over fq, so it'll have some dimension, let's call the dimension n, then it also satisfies a functional equation. Okay, so this is rather wonderful. Okay, so what's the functional equation? Let me write it down here. So the functional equation happens when, instead of evaluating this zeta function at the t, we are going to evaluate at 1 on q to the nt. So q, of course, is giving you the finite field that we're working over, and n here is the dimension of the variety. So it's going to be some scalar multiple, or some multiple of the original zxt. And that multiple is given by this expression here. It's just a polynomial in q and t, plus or minus q to the ne on t times t to the e. And what is this e? And this is the bit where it gets really, really interesting. This e here, actually, you can say something, and it's related to the topology of what happens when you try to look at this variety over the complex numbers. So you can look at the complex points of this variety of x. So if you can do that, okay, so suppose that you're in a situation where you can do this, okay, then it's just the Euler characteristic of that. So I guess that should be also a hypothesis in there that you can look at this over the complexes as well. Okay, so this is a rather remarkable thing. So let's just check that it holds in the one case where we've computed the zeta function. Okay, so let's have a look here. So in this case here, n is equal to 1. So you evaluate at the variable 1 on qt. So if you put inside here, okay, the zeta function, instead of t, you have 1 on qt. The q's will cancel. You get 1 minus t inverse for the first factor, 1 minus t inverse. And in the second factor, well, this t is just the inverse of qt. So it's 1 minus q inverse t inverse. What we want to say is that essentially it's just up to multiplication by a single polynomial like this, okay, a monomial in fact. It's just the original. So what we'll do is we'll just clear the denominators on the top and bottom. So to do that, we'll multiply, to get rid of this t inverse here, we'll multiply top and bottom by t. And to get rid of the q inverse and t inverse, we'll multiply top and bottom by qt. So at the end of the day, you've multiplied by qt squared. And then what you'll have here is you multiply by t, you get t minus 1. You've multiplied by qt here, you get qt minus 1. Of course, the denominator is essentially just the same as the denominator here. You've just swapped terms and you've negated both of these. That will cancel. And the numerator rather has changed by a factor of qt squared. Okay, so that's what happened. When you evaluate this 1 on qt, you'll get the same thing except for you've got this extra monomial term here. And let's check what this monomial term is. Okay, so the first thing is the projective line. Okay, if you look at the projective line over the complex numbers, so what is that? So firstly, you have the affine line of the complex numbers. So the affine line is just a copy of the complex plane, and you add a point at infinity, so you get the Riemann sphere. So here you're looking at the Euler characteristic of the Riemann sphere, okay, or sphere, and that happens to be 2. So here you have t to the 2, so that's t squared. Okay, here you have n, your dimension is 1 times e is 2 divided by 2, that's 1, so you just have a single q. And it turns out the sign that you have here is a plus as opposed to a minus, so you get this. And that's how the second part of Weil's conjecture, the functional equation, works for the zeta function of P1. I hope you enjoyed this adventure in pure mathematics.